Okay, so just looking at 1 minute papers from last time, there's a very good question, which is why Agda is perfectly happy with this definition. Why doesn't it moan that the recursion in forever is infinite? And that's because it's supposed to be infinite. Let's figure out what the obligation is here that Agda is actually checking. So when you write a function which consumes inductive data, like fold R or something like this, Agda is checking that the recursion terminates. It's checking that recursive calls are on structurally smaller inputs. But when Agda is checking co-recursion, as we call it, it's not not hoping for termination, and it's certainly not going to complain if it doesn't see it. It's hoping for something different. It's hoping for productivity. So what that means is that it must always be possible to answer the questions that are demanded. So here we're saying streams have to be able to tell you their head and their tail. And so the question is, have we done enough to ensure that for a forever stream, we can always tell the head and the tail? And you can see that yes, we can always tell that the head of forever x is x, and we can always tell that the tail of forever x is forever x. So whatever demands turn up on forever x, they will always be satisfied. So Agda is happy. You should also be aware, one reason why co-pattern definitions are really cool is that these equations are really true as far as the type checker is concerned. And you'll notice that there's no equation that just defines forever x, right? If I ask it to evaluate forever 3, it just sits there being forever 3. There's no equation that says forever 3 ought to compute to something. Instead, the equations tell you what happens when you look at forever 3 in some way. That's to say, forever 3 will not compute at all unless there's some demand to see what the initial part of it is. So we can ask what is the first of head tail of forever 3, and it'll say that I did open stream. What's it whinging about? Let's try that again, only with first of stream.headTail of forever 3. It says that's 3. When we say, what's the first of the head tail of forever 3, it then expands correctly. Let's see what happens if we just ask it for stream.headTail of forever 3. That doesn't expand either, because we don't have an equation that says what head tail of forever 3 ought to be. We only know what the first of it is and what the second of it is. So we're protected from accidentally running an infinite computation for an infinite amount of time by the fact that they only unfold on demand, and the program that's using forever 3 can only ever make finitely many demands in the course of its execution. So that's the trick to it, that it's not going to aggressively generate an infinite sequence of 3s. It's just that you can have the next 3 whenever you ask for it, but you have to ask. Okay? So that way, these apparently infinite computations aren't actually infinite. They're merely, they're driven by demand, and the demand will always be finite, simply because there's a finite amount of time in which to make demands. So that's kind of cool. So we often see, we saw this with our co-inductive applications. We don't say speculatively an application should run forever. We just say an application should respond whenever you poke it somehow. And that's enough to allow us to give a sensible runtime to an application. So it's one of those things. There's a long-running propaganda war about what's called total functional programming. That's to say, programming where recursion always terminates and co-recursion is always productive. And there are people out there, and you know who you are, who carry on telling lies about when you need general recursion. In particular, anyone who has ever said in a talk, and you do know who you are, that you need general recursion to write a server, you know that's a lie, and you knew it was a lie when you said it. So fess up. Hello, television land. Right. So there's a whole world of that nonsense. There's often people out there who say that Agda is, because it's total, it's not Turing complete. But that's to say, somehow you can't explain how to simulate a Turing machine, because Turing machines might not halt, right? Now, what's the deal with the Turing machine? That they might not halt. So correspondingly, the computation of a Turing machine is a potential infinite object. You might, for example, define the co-list of the states a Turing machine passes through while it executes. And you can perfectly well explain how to see the next state if you want to. The usual deal with running a program is that, while you're willing to feed it electricity and wait for it, it can compute for as much as you like. That's to say, while you keep demanding behavior of it, it keeps producing behavior. And that deal is perfectly well available with co-recursion. That's what we've been saying, that you explain how the process responds to demands, and then it's willing to keep on delivering behavior as long as it gets demands. That's the ordinary deal. The one thing you can't do with a total language is lie about infinite things being finite. You can't say a potentially infinite list is bound to stop, because it's not. That's a lie you can't tell. But in exchange for not being able to lie, what you can do is tell the truth. And languages with general recursion are incapable of trustably telling the truth. The expressivity failure is exactly on the general recursive languages. They can't be trusted. You can't make promises in a language with general recursion the way we can make promises in Agda. But we can implement all the same systems that general recursive ones can. So let's be clear. Who's got the problem about not being able to do stuff? Not us. All right. Enough propaganda to the camera. Let's do something slightly different today that will connect back to where we're at. I want to introduce a crucial concept, which is the concept of a universe. We've already seen a few things a little bit like this, but it's worth focusing on it. I'll start with the smallest interesting universe. Oh, I haven't got 2 in scope. I'll give myself 2. So a universe is a collection of types, and the types get collected in a particular way. We're going to talk about some of the types that are available, and we're going to do it by picking them out as the image of a function. So I have my data type of booleans, true and false, and I define a function from the booleans into set. So that means I can actually pattern match on my boolean and decide which type to give back. And so the idea here is that we want a type which represents the evidence that the boolean is true. I could just use being equal to the constant true, but I'm going to use the power to compute with this data type instead to say, what evidence would convince you that true is true? Well, hopefully it wouldn't take very much evidence. What evidence would convince you that false is true? There is no evidence that would convince you of that. So we've taken our smallest 2 types, 0 and 1, and coded them up, given data representations for them, just by using a type of booleans. So there are various things we can do now. One thing we can do is maybe define is 0 from that to 2. So we can define some boolean test. Actually, maybe I want is suck. Let's have is suck. Often more useful. So that's going to be false, and that's going to be true. And then I can say, I don't know, maybe I need to say something like, if I was going to write divide for all x and y in that, so is, I'm not actually going to write divide, but the sort of thing you can do is if you want to say that the inputs to a function must pass some Boolean test before you're willing to compute an output, then you can make use of this universe just to say, well, you better give me the evidence that that test is passed, as well as the inputs themselves. So if you look at y, and y is 0, then guess what? We smell a rat. The test failed. This can't be happening to me. So that's one use of so, and we'll see some others in a moment. So we've built our first universe. We've used the Booleans to code up a type that must be 0 or 1. And although we can't pattern match on types, we can pattern match on Booleans. So if we know our type lives in this universe, that's to say, if we know we have a Boolean code for this type, it's as if we can pattern match on types. And that becomes quite useful. Let's have a look at the sorts of types we've been writing, right? Things like 1 plus x times t and stuff like that. We might decide to build a slightly more flexible universe. We might give ourselves a data type of polynomials. And we could say, well, we have variables, and we might allow ourselves 0 and 1. I'm actually going to do that by introducing the constants, which in traditional style I spell with a K. So the constants are polynomials, and then I'm going to have things called plus and times, and I put quote marks on them, which take two polynomials and give us a polynomial. So at the moment, all I've got here is a data type, a perfectly ordinary data type with I'm just writing down a data type that represents a syntax of polynomials. But to get my universe, I need to say which types the syntax stands for. All right, so let's do that. I can say, I can write a thing called eval, which for all x in set, if we know which types the variables stand for, then we should be able to say which type of polynomial stands for. Actually, I'm going to put a quote mark on that. And then I'm going to call this thing var p. Okay? So somebody passes in the meanings of the variables interpreted as types, and then we have to give the meaning of a whole polynomial. What do we do? Well, there's 4 cases. If the polynomial is just a variable, we'll interpret it with the function that's been passed in. If we've got a constant, I'll change that to a b. Then I'll interpret it with so. And if we've got the sum of 2 polynomials, I'll compute an honest to goodness choice. And if we've got a product of polynomials, I'll compute an honest to goodness type of pairs. So we've now given a coding system for types that are built up with 0, 1, plus, times, and variables. One thing we can do for amusement is to define all of the data types that can be given by polynomials at once. This type is often called mu. So we've got p, we're going to have one variable in our polynomials. There's going to be a constructor like this. And what do we have to give to make a mu p? We have to give the result of evaluating something at p, evaluating p. And here I have to say how to interpret the one variable that we have. And I'm saying we interpret the variable as a recursive reference to mu p. So that's to say, we write down a polynomial that describes the node structure of the data, and each set of angled brackets packs up one node interpreting the variables in the data as substructures. So in particular, if we, well at the moment, because I've only given myself one variable, I've got a little bit of a difficulty. I can't write lists down, but I can write natural numbers down. I can say nat p lives in poly 1. Okay, and I need to write down the polynomial which describes the node structure of natural numbers. Okay, what is the node structure of the natural numbers? Well, you either have a 0 or a successor, so that's a choice. Okay, let's take 0 as going left. Does going left, does 0 carry any other data? No, it doesn't. So we can finish that off with a constant true. That will give us just a boring empty node. Meanwhile, how about successor? Does it carry any other information? Yes, it does. It carries another number, the predecessor. So there we can say, let's have the variable. And now I can take nat to be mu of nat p, and if I want to define 0, I'll just call it z. I think well, let's define it as a definition first and then turn it into a pattern synonym. How do I make the thing that behaves like 0? Well, first of all, it's definitely going to be a node. So I'll pack it up in angle brackets. And now I have to choose go left or go right. So I go left. And now I just have to give my trivial thing. How do I build a successor? Well, again, it certainly has to be a node. This time I go right. And now I'm asked for another number, because that's how variables are interpreted, as recursive substructures. So I've been able to reconstruct the constructors of nat for a data type whose code we gave as a polynomial. So what's going on here? We are used to declaring data types with data declarations. And data declarations have a hardwired syntax that allow us to offer a choice of constructors that pack up various pieces of information. And what we've just done is stepped away from hardwired data types. We've got ourselves the ability to define a single universal data type, which allows us to give all of the data structures that can be given a code. So I could just as well define the trees. What's the node structure of an unlabeled binary tree? Well, it's either a leaf or a node. So I'm going to offer a choice. If we go with a leaf, then that's going to be a constant. And if we go with a node, then we should have a pair of subtrees. So that's going to be something times something. And now we want subtrees. So that's going to be a variable standing for a recursive position on the left, and a variable standing for a recursive position on the right. So what we're saying is, if we refer to the variable colloquially as x, right? That unlabeled binary trees are generated by the functor 1 plus x squared. Oh, I just said it was a functor. I better come good on that, at least to some extent. Let's write ourselves a little operation. And let's suppose somebody gives us, do I want to do this? What do I want to do? I want to have 1x, and I want to have u and v both living in x are a set, and then p in poly x. Those are the data that come in. How would we turn an eval, I should call these lowercase things u and v, an eval up into an eval vp? Well, I would need to know that for every x, I can turn a ux into a vx. So all I'm saying is, if we change the meaning of the variables, but we know how to translate from the input meaning to the output meaning, then we can push through the structure. So let's see that. So eval u, v, p, f, x, question mark. And we do this by recursion over the structure of the polynomial. And now I get some annoyance. Let's call that I, that B, and these things Q. Change the names. Okay. So if the polynomial says that we have a substructure in this position, then what does that tell us about our input? It tells us that it's in whatever type u says it is. And we need to give out whatever way v interprets that variable. But fortunately, we have a function that turns all the u's into the corresponding v's. So that's going to be f(i)x. Okay. If we've got a constant, then we're in the situation where we know actually the variables don't matter. We've got an element of so b. We need an element of so b. We can give it straight back. Now what happens if we've got, if our polynomial is a sum? Well, we know that we've got an eval up or an eval uq, so we can see which of those it is. And in this case, we know that the input went left. So guess what, folks? The output also goes left. If the input goes right, the output also goes right. You'll notice there's no choice about what to do here. There's really only one thing that could possibly work. Similarly, if the polynomial describing the data says it's a pair, then if I look at x, it's a pair. And in that case, we have to build a pair of outputs. So here, one of the inputs to this function is describing the data structure that the later one is stored in. And we're making use of that data structure description to compute what we need to do. So this is a weird thing that you might hope is sort of sensible. how often do you encounter things like a file format, or a grammar, or a database schema that's just a piece of data, and you get told, here's a lump of data which is a format descriptor, and then here's some data that matches the format. That requirement that the data matches the format, which is also data, is beyond quite a lot of programming languages, but it's perfectly manageable here. So that's kind of cool. So we've been able to implement this sort of map operation for node structures. We ought to be able to implement a general purpose fold operator that works for mu. So let's see if we can do that. Let's see what it would be. Fold for all p in poly 1. Right. How does a fold work? There's going to be some type we're trying to compute, and we're going to try and compute a t from a mu p. So t is our output type, and p describes our data structure. We've got some raw data given by mu p, where p gives us the structure of the whatever it is. Okay, how does a fold work? You give an algebra. You assume that the recursive substructures have already been turned into t's, and then you explain how to finish the job and compute the t for the whole node. So that means we need something which interprets variables as t's, but has the structure given by p, and it gives back a whole t. And then at this point we have a fight with the termination checker. Right, we look at our x, and we can see that our x is a node full of data, with substructures still represented as raw input tree structures. Our alg will give us a t if only we can figure out how to process the subnodes. So we can certainly start by saying it's an alg of something. And now we need to turn all the mu p's inside x into t's. Hang on a minute, we just wrote map for all of the polynomials at once. So let's use it. We want to start interpreting variables as mu p's, and I'm going to need to bring big T into scope. We want to finish up interpreting the variables in the polynomial as t's. The polynomial itself is p, and then I need to say what to do, and I need to give the data in. That's an x. Okay. And now what do I have to say? How to turn an individual mu p into a t. I've got to abstract boringly over the one variable that there is. And then what I'd like to say is fold p alg, at which point the termination checker will scream at us. The termination checker does not understand that eval really will only use a recursive call to fold on a substructure. You know that, I know that, Agda doesn't know that. So at this point, I scream with rage and reluctantly specialize map to fold. So there's something that needs to be done quite carefully. I'll do it and then I'll explain it. Right, now here, let's see if this is fit for purpose. I'll say eval fold and I'll kick it off with the polynomial p and an x. And that's good, okay. So what did I just do? This is not my first rodeo, so I avoided a problem. I want to turn a p whose substructures are mu p's into a p whose substructures are t's. Why did I abstract over this extra q? Actually, maybe I should just show you what goes wrong. How about that? I'll call that p, and I'll change all the q's to p's. Everything still type checks, but I'm actually in deep trouble. Let's see why. Here you can see that I've got to give back I've hit a variable, and here that's where I'd like to process a substructure by a recursive call to fold, but I don't know well, for one thing, my algebra talks about this p, which is this one, not about this p. So maybe I have to dig myself in deeper, copy that, paste that in there, and then I have to give myself an algebra everywhere. Fun to go wrong. Oh, and then I have to give the algebra there. What fun. Okay, this is now going to work. At least it's going to work up to a point. Now I can say fold you can see I've got my local copy of the algebra will allow me to do a fold var prime. That's my polynomial, and I've got my algebra for that and an x, and it buys that. So where do things go horribly wrong? They go horribly wrong in the plus case. Right. Now what's happening? The overall polynomial is some choice. So I need to see whether I go left or right. That's fine. And if I go left on the input side, I'd better go left on the output side. And now I want to post-process. I know I've got a P structure on the left. I need to give an algebra. I'll think about that in a minute. And now I've got a problem. This thing won't even type check. I know that the node structure I want to process is a P, but Y was given this variable. It's a P, but its substructures are P plus Q, because the original polynomial was a P plus Q. So what's going on is this. I'm trying to take apart the structure of the top node a little bit at a time. And I've made the mistake of saying that the structure of the subnodes is always the same as the structure of the part of the top node I am looking at. But as I focus in on, as I take the top node structure apart, that means my assumption about the substructures is shifting under my feet. And that's where things have gone horribly wrong. So let's get this right. I don't want to abstract over an extra copy of the algebra. And I'll go back to where I was. I should call this Q. And I should take that out of the way. So here, Q stands for the part of the top node I am currently looking at. Q can get smaller and smaller and smaller, leaving P exactly as it is. Here I'm saying all of the substructures are trees who's given by polynomial P. No matter which part of the top node I'm looking at, the substructures stay exactly as they were. And that's good, because those are the substructures that I know how to turn into T's. So that's a classic lesson. This happens sometimes, that when you're building a helper function, sometimes you need to take effectively two copies of some important information. One to take apart, and the other one to keep as it is. Imagine like writing division by repeated subtraction, or and then subtraction by taking one successor off at a time. If you're dividing by n, you need to count down from n to 0 each time you do a subtraction. That's given by counting down from n to 0. But when you've finished that subtraction, you need to subtract n again. So you need two copies of the thing you're dividing by. One to count down to do the subtraction, and the other to kick off the next subtraction. So it's the same deal here. We've got to have one P that stays fixed, that tells us what the substructures are, and one Q to tear apart. And we kick them both off. We kick off Q by being the whole thing. So this happens all the time. Right. Okay, so that's going to be that, that's going to be a B, that's going to be Q and R, and now we should be laughing. This should be fold P alg X. We can now make a recursive call to X, and Agd is happy with that. This, we got to, you can see I'm just implementing map again, which was the point. So we've been able to write fold. You can see eval fold is exactly our general purpose. At least you could, maybe I'll give myself two windows. What is eval fold? Eval fold is eval specialized with f being fold. And the only reason I have to do that is so that here it's clear to Agda that when we make our recursive call to fold, it is genuinely on a substructure of the original data. So that's a source of frustration that you have to do that. So let's see where we're at. We've got polynomials and we've turned them into data types. We could just as well turn polynomials into co-data types, and the traditional name for that is mu. Mu for data, nu for co-data. And then we say, what do we get out when we look at the top node of a co-data structure? We get an eval where the variables are interpreted as subdata. We get a node with with recursively instantiated variables as the substructures. So again, I don't have time, but I could build an unfold that would take a co-algebra for P and generate a new P from it. And again, to satisfy the productivity checker, I would have to write an inlined implementation of map. That's to say, this eval thing for the polynomial. But why do we care about doing this? Well, the crucial thing is that now we have a data type. Here's polynomial. It's a perfectly ordinary data type. It's got lovely red constructors. We can pattern match on it. So if I want to say things like, you can see that all of the structures we can possibly build with mu p are all finite. Each node only grows a finite amount of stuff. It ought to be possible to implement, let's say, an equality test, not for one data type in particular, but for all of the data types describable by polynomials. And we do that just by looking at the structure of polynomials. There are all sorts of operators. Maybe we want to generate something like size, just measuring the number of nodes in a recursive data structure. Again, that's something which we ought to be able to do, not for one data type in isolation, but for all the data types describable by polynomials. So once we give ourselves a data type that encodes for a whole system of data types, we've got some serious power tools. We can say there's some standard kit that ought to be available for every data type with an encoding, and then build that once for all. So that's the crucial thing, right? You know in Haskell, when you declare a data type, and you can say things like deriving eq, right? What happens when you do that? Well, what happens is that a little bit of the compiler, a little bit of GHC, goes away and manufactures some source code for an instance declaration for an equality test for that type, and then tries to compile that. And if, for whatever reason, the generated source code doesn't work, you actually get an error at at that stage. And that sometimes does happen if your type is weird enough. The deriving EQ feature is hardwired in the Glasgow Haskell compiler. There's a fixed repertoire of type classes that it knows how to generate the code for. If you want to do that yourself, right, then it's a lot more tricky. Whereas here, we're in the situation where we can write our own deriving. We've got a first-class notion of data type description. So we can write our own deriving mechanisms to give functionality for every type with a description. One thing I'm going to look at on Friday is a particular piece of functionality that we might care about, which is how to describe the contexts in which you can have a subtree situated. So what is it like to be, let's say, a binary tree with one subtree missing? What's a big tree with a small tree cut out? An amputree. Right, what's it going to be? You're going to need to remember the path back from the particular subtree to the root. But you're also going to have to remember all of the other stuff that comes off to the sides of that path in order to have the full context for the subtree of interest. Why do we care about that? Well, if we happen to be editing a tree, we might have a cursor that moves around the tree structure, and there will always be one subtree where the cursor is at, and then the context where that tree is sitting. And we might want to be able to say, replace the subtree where the cursor is with something different. So it's a useful structure for editing to be able to say, what's the context? And guess what, folks? If you know the polynomial that describes the overall data structure, you can calculate from it the data structure that will give you contexts. And it turns out to be one of the oldest computer programs that human beings know. It's not 3,000 years old like Euclid's algorithm, but it's a good, solid 17th century program. It also happens to be the first program that was ever written in pattern matching style in a functional language. More about that on Friday. Let's stop there.